So far, we have talked about resource management, user management, and their interaction, right? What does all this mean to a data scientist? So usually, as a data scientist, you will not be involved in provisioning or managing any of these resource management or access management activities. However, you will request the administrators in your company to provide you with access to certain resources or privilege to provision terminate certain resources. So in that case, it's better for you to understand that you will log in as a group, or if you're running through Azure Virtual Machine, it will be a VM managed identity. Or if you're running this on your own machine outside of Azure, it will be a service principal. So then you also need to know that you are requesting a role connected to your principal or user group, and you need to know what privilege your role will require. So this is all you need to do. You need to understand this terminology. You need to understand how this work together. So it's very useful to understand what is behind all these requests. Now, let's provide a quick summary of previous weeks. We had introduction to cloud. We have discussed about virtual network in the virtual machine. We talk about serverless computing, container function as a service, API. We talked about storage, blob storage, and file storage. And today we talked about cloud resource management and user management. How are these related to data engineers and data scientists? These are the fundamental services provided by Azure. So far you see we have the storage, you have your data saved somewhere, and you have a compute, you have a virtual machine that can run Python notebook. So that's good enough for most of the data engineers to start their job, right? These are fundamental services that are widely used in data engineering and data science as a fundamental service. And they are good enough to create a data science project or any projects. So with that, there are also data-specific services provided by Azure. Azure provides you with out-of-box services that you can utilize. It manages the infrastructure for you, such as the serverless, right? We talked about infrastructure as a service or platform as a service. Azure provides you with a platform that you can upload your data and perform your own execution. In a typical enterprise. The data flow starts with the data sources, enterprise application. Usually these are transactional systems like ERP, CRM, these words, but think about like in the e-commerce website. The transaction system will be the the order processing system, right? You click on a button, buy, then the order is submitted to this transactional system. The transactional system will record down your order and send that, store that in the data file somewhere, or database somewhere, and then you will use the extract, transform, and load process. You first read that original raw data from the data source. Then you will transform that and save it to a enterprise data warehouse. Inside this data warehouse, usually sometimes you organize it by third normal form, sometimes you organize by star schema, but that's where you have all the pieces of your information, all the data you collected from the company stored here in this enterprise data warehouse. That's the central deposit of all data you generated in this system, in this enterprise. Then based on your analytical needs, you will extract pieces of information from a data warehouse and form data marts. One data mart, two data marts, three data marts, each with a different purpose, and send that to final users for analysis. These users can be data analysts, data scientists, reporting specialists, miners. They just read information, read data from the data mart, which is built on top of enterprise data warehouse. So this is the traditional, typical enterprise data flow. So when you have data inside your database, you need to have a certain way of modeling that. It's in a sense similar to resource and user management. When you have a lot of elements, you need to organize it in a clear way. And that clear way usually requires some overall view of the data and a methodology that you can use to handle the data. So that is called data model. A data architecture describes how data is managed, right, from collection through to transformation, distribution, and consumption. To collect, store, and analyze the data in the computer system, a well-designed data model is necessary. How you would organize the data, how you would define a relationship between different data elements. That's what the data model is. Data modeling is about to resolve. Data modeling, starting with hierarchical, there are many different ways of the data modeling. The most common ones, hierarchical, network, relational, and dimension. Let's talk about this one by one. So, but first, we are not starting from data model. Rather, we start with the transactional system. The transactional system comes with usually are called online transaction processing system or OLTP. These are source systems that generates the data of your business activity. Those are like enterprise applications like ERP, CRM. CRM stands for ERP stands for Enterprise Resource Planning. It basically contains your like human resource, your human resource information, your facility utility information, facility information, and your computers, servers, all this, managing those the daily operation. Then there's CRM, which is customer relationship management, where you define your customers, lock down their information, and planning campaigns, marketing campaigns, processing their orders, and finance, of course, handling the monies ins and out of money. Then there's e-commerce system. E-commerce systems such as Amazon, right? Amazon or Walmart, where they sell big time online. And then there's social networking sites where everybody is familiar with posting your posts or give likes or dislikes to other people's posts. And finally, Internet of Things like cell phones and the smartphones is generating data, uh, keep on generating data every second. So these are the sources of the data, and the data comes from the source. Many source data are hierarchical based on the nature of data flow. For example, we talk about e-commerce. In the e-commerce, so when you make an order, right, very likely you have multiple items in the order. Three items, like if you make a purchase of toys, maybe one toy for a boy, one toy for a girl, and then a book for yourself, something like this. Then this is hierarchical structure. One order with each order have multiple line items. Sometimes it's one line item, but many more times you have more than one line item. This is a hierarchical nature model. And similarly, course and student. Each course have multiple students. So this is naturally many source data comes as hierarchical, and hence the hierarchical model is a natural design pattern based on the data source. It's going to be records with sub-records inside it. But the problem with hierarchical data model is that sometimes it's not always if you just try to analyze the data through the hierarchy, that's perfectly fine. But what if you want to do some cross hierarchy analysis? For example, student, right? Course and student. Yes, there's a bunch of students in this course and a bunch of students in that course. If I want to analyze the average grade of this course, that works. If I want to analyze the the student evaluation in another course, that's fine too. However, what if one student enroll in multiple courses and I want to analyze the performance of that student? Then I have to go through all the courses to identify the courses that this student is in, and write down his or her performance to get a proper evaluation. So this is where you have a network database data model come up. Each subworker may have its own real-world mapping, right? So which is beyond hierarchy. So products exist or without orders, student exists with or without a course. Hence, network model was invented. The problem with network model is that without a clear mathematical way of defining, you can arbitrarily draw connection relationship between any two objects. So how do you clearly define the relationship between different components in a simple way? That's easily understandable, but you are not losing any real world relationship, right? So the network data model is usually considered too complex and hard to maintain. That's when we have the so-called the famous relational database, the relational data model. It was created in the 70s, right? You can define all data as sets. Here, this word set it's a mathematical sense that it's each element in the set, each item or instance in the set has the same fixed schema. When we say fixed, not only the schema, the content is defined, but also the format and order are defined. So it's easy to think about data sets as a two-dimensional table and they can be joined together. Now, I believe all of you in this class should have already learned SQL and are somewhat familiar with the relational data model. So I'm not. So this is provided just as a way to recap what you already know. Now, after so when you have this hierarchical database, you have a network database, and you have the relational database, and you can consider how data are structured. When data comes in as a hierarchical data, right, it's semi-structured. We call it semi-structured. They don't have a rigidly defined structure as a traditional relational database, but still remains some form of structure. For example, JSON data. Inside the JSON document, there are a bunch of key value pairs. So for each value, you know what the key is it belongs to, right? So there is still a schema. However, the schema is not the predetermined schema. Uh, Within all the JSON documents in one file, you can have some documents with a certain key, some document without that key. Similarly, for XML, some fields can be missing from certain nodes, right? So these are and the order of these keys can be different. You can have last name first, you can have first name first, you can also have social security number first. Either way, it's not going to impact the content of the JSON for a file or XML document. So overall, this is what we call semi-structured. It has some structure, but it's not entirely enforced. You can have missing fields and you can change the order. Whereas in a structured world, structured data are highly organized and formatted, typically fits into rows and columns following predefined schema. And that predefined schema may very likely be defined. Its order, the order of attributes are also defined. So there finally, so a good example of that, of course, is relational database. That's exactly what a relational database is about. That's usually, but of course, data don't naturally come this way. It has to be processed in order to fit into this fixed schema thing. With that, there's also something called unstructured. There's no clear organization or format. For example, like free text documents, like Word files, PDFs, or social media posts. Nobody cares about grammar when they post on social media, right? And there's multimedia content like image, audio, video. But inside all these the data, till this day, relational database is still the most important database in any enterprise setup. It's widely used for many tasks, including both transactional tasks and analytical tasks. Um, Relational database has a lot of advantages, right? It's built on top of a solid foundation of relational algebra. And in my opinion, this is the most important thing. All other advantages actually come from this one. Because you have a simple and clear mathematical foundation, that's why you can have a generic model to fit into as many situations as possible, right? As you may run into. You have a generic model that can fit in many different scenarios because your system is based not on practical experience but on some mathematical equation that is more flexible and more abstract that you can ignore more unimportant aspects of modeling. Then you also have a simple and universal operating tool, which is a structured query language, SQL. And this is also introduced by the foundation of relational algebra because you can use a certain way of operations in a mathematical algebra. That's when you can translate these operations into a structured query language. And with these all three advantages, the relational database quickly gained momentum once it was born, and now it has a full ecosystem with established vendors and a community. Any relational database on the market, you go there, you will see someone's using that, and you can find some kind of support. And this is very important. If you are utilizing some small scale tools, it's very hard to get the support, and it's hard to understand what the behind the scene they are doing. But for a relational database, we pretty much know how it's implemented, and we know how it's managed. So it's easier to figure out ways to fix issues or to achieve what we want to achieve. And finally, this is used so long, so it's well understood and have a very large user base. And this is important because you have more. No, for one thing, you have a more support and a larger knowledge base. And two things is that as an employer, it's easier to find people with these skills. So when you implement your system, of course you want your system to be easier to maintain. One very important thing about this maintenance is easiness of maintenance, is how easy you can find someone to replace your current team if they ever decide to leave, right? And this is perfect from the SQL perspective. You can easily find people with SQL skills in the market. So the next thing we want to talk about is a star schema. So we talk about relational schema for so much. It can be relational, but the relational schema originally comes as a way to handle transactional systems, right? You see, it's marked trace marks from hierarchical data model and network data model. But over the years, it evolved so that it can also support analytics. But they are not always the best choice in all analytical scenarios. They are optimized for transactional workload, especially like asset maintenance. We will talk about asset next week. It's not always well suited for complex analytical queries that involve aggregations, joins, and filtering. For analytics, dimensional model is a better model. It organizes data based on business activities, which is the main subject of data analysis. In a dimensional model, data is centered around the measurable attributes of the activity, such as amount, quality, these are usually called fact. The measurable and the calculable, computable attributes of the activity, like sales amount, the dollar amount, or the product quantity. And then data is aligned based on dimensions, attribute hierarchies. Those are attributes that are descriptive regarding a certain fact. A star schema is a type of a data warehouse schema used in the design of data warehouses in the business intelligence systems. It organizes data according to the business activity that is analyzed. It's a specific way of organizing data to optimize query performance, reporting, and analytics. Then also it's a variation of relational data model. All data in star schema are still relational tables meeting the first normal form requirement, but they're not necessarily third normal form compliant though. So here is the star schema, right? We mentioned there are two types of attributes when you define a schema, star schema. One is those that you can add, you can calculate, like this total cost, quantity, and the sales amount. These are calculable, computable. Those are like aggregatable. You can perform a numerical calculation on top of that. So this is the fact table. But just have a amount does not provide enough context. So there are attributes that providing the context, like what product it is, what's the which day this happens, and which employee performed this sale, etc. And this information all usually stores in auxiliary tables called dimensional tables. They form dimension and they stored in dimensional tables. These dimensional tables can be joined to fact table through the dimensional key. Thus, when you have fact table in the middle and all the attributes tables joining to it, remember attribute tables or dimensional tables, they don't join with each other because they are all a descriptive field of the same fact. They are different aspects of the fact, so they don't join each other. They only join with fact. So fact table. So in the end, it will be a fact in the middle, a fact table in the middle, and a bunch of dimension tables standing around it, thus forming a star-like schema. This is where you get name star schema. The design principle for star schema is what we call a Kimball Enterprise Bus. It's a conceptual framework. It's a concept and framework for organizing and managing data within an organization, especially in the context of a data warehouse and business intelligence environment. It still comes from the same idea of having facts, focusing on starting of storage of facts and focusing on attributes that describe the fact. What you will going to do is you will identify the business activity, and for each business activity, how many business activity exists in an enterprise. For example, if it's a pharmaceutical company, of course you have the sales. You have people visiting doctors to sell their drugs. Also, you have the manufacturing part, where you have people working in a factory facility to create manufacturing these drugs. So these are business activities, different business activities inside the company. Your job, the first job in design star schema using Kimball Enterprise Bus is to identify these business activities. Then for each business activity, you will define the facts and dimensions. You will see inside this business activity what is measurable. If you are manufacturing the drug, what's the cost? What the raw material? How much raw material did you put in? And what's the output? And what's the cost of each product of each, let's say, each pill? Then how much do you sell it, and what's the profit you get? These are the facts. These are computable, aggregatable numerical values. Then around this fact, you define the attributes. How do you define this fact? So, for example, I have a selling amount of $200. Where are these $200 come from? It happens in the sales that someone performed in CVS or Walgreens at a certain day, this day, right? So these are the attributes that describe this sales fact, the location, the time, and the employee involved, etc. Then you will organize the facts and dimension to build a matrix of fact dimension relationship, and you will optionally consolidate facts with same dimension. For example, here, right, this is row is each row for if you have a business process like a customer billing, and what does this fact, what the attributes can use in describing this event. Of course, the time happening in the billing, which customer is involved in this billing, and what the service is about this billing, and what's the rate, and provider, which provider provided it. Of course, there's no call, so there's no calling party, no call party. Then there's also long distance to provider, etc. So you identify out of all these attributes, which attribute can describe this fact. And you do this again and again for different business activity. And eventually, you get this, what we call an enterprise bus. Each row in this bus can form into a star schema. It will be custom billing fact with all these 1, 2, 3, 4, 5, 6, 7, 8, 8 attribute dimensions. So you will draw something like a fact table and the 1, 2, 3, 4, 5, 6, 7, 8 the dimension tables around this customer billing fact, thus forming a star schema. So as you analyze the business activity, it naturally guides you into designing a star schema.